Okay, in this section we're going to be discussing addition of a system of coplanar forces. So basically what this is resolving a vector into its components, the x and y components, and that makes a simple way to add multiple vectors together. So this is our x and y axis, and we have a force F at an angle theta. Our x component, Fx, and our y component, Fy, can be easily determined. So Fx would be equal to F cosine of theta. And Fy would be equal to F sine theta. Okay, now the other way that this can be looked at is, let's say we had x, and this time let's draw a negative y. And F goes down like this. And instead of an angle this time, say that we're given a slope. So this is A, this is B, and this is C. So now if you want its components, Fx and Fy, you can find them using the slope. So that would be Fx would be equal to F, and it would basically be cosine theta. So cosine theta is going to be adjacent over hypotenuse, which in this case is alpha over Charlie, so A over C. And Fy would be a negative F, because the y is in the negative direction, times B over C, because sine theta is opposite over hypotenuse. So the same thing, it's just using the slope formation rather than the theta formation. So now the other thing that you can say is that x is also equivalent to an I vector, and the y is also a j vector. So I being just in the x direction, y being I being in the x direction, j being in the y direction. So if we wanted to write a force F, a vector, we could say Fx, so the scalar component, in the x direction, so that gives it a vector notation, plus Fy, the scalar form, just like this, in the j direction. So now what we can do is we can do a F1 plus F2 plus F3 is equal to the resultant force. So let's say it looks something like this. We've got F1, F2, and F3. So F1 can be written as F1xi plus F1yj. F2, same thing, except that we would write F2xi plus F2yj. F3 would be equal to F3xi plus F3yj. So now if we want to add all these together to make our FR would be equal to the components of each one of these. So F1xi plus F1yj plus F2xi plus F2yj plus F3xi plus F3yj. So now combine like terms, aka all of the i's. So we would get FR is equal to F1x plus F2x plus F3x multiplied by vector I plus the scalar F1y plus F2y plus F3y multiplied by the vector j. And so this can be combined to just say FRX, the x component of the resultant force, and FRY, the j component of the resultant force. So we could write the final vector FR as FRXI plus FRYJ. So this kind of shows you how these can be combined using the I and j vectors to get your FRX and FRJ. So normally what I do is instead I start from the beginning, I would say, okay, all of the x components, which means that FRX is going to be equal to F1x plus F2x plus F3x, which is basically just that the FRX is always going to be the sum of all your x components of the forces. And your y is FRY equal to F1y plus F2y plus F3y. Same thing, the sum of all your y forces. So now, your resultant force, you have FRX and you have FRY. So it's basically the parallelogram law again, in that you can make your parallelogram FRY, FRX, and you get FR. Now this is the special case where it's a right triangle, since x and y are right angles from each other. So if that's a right angle, then FR can be solved using the Pythagorean theorem. So the square root of FR is equal to the square root of FRX squared plus FRY squared. Also, if this is equal to theta, you can say that theta is equal to the inverse tangent of FRY over FRX. So what this ends up being is a simple way to resolve all your components of your vectors, add them together. Once you get the x component and the y component of your resultant vector, then you can use the Pythagorean theorem and your tangent to come up with the magnitude and direction of your resultant force.